Hi, I'm Matt, and in this video we're going to talk about what a derivative is and how it is notated. So first, before we get into derivatives, I want to give a quick discussion about what secant line and tangent lines are. So a secant line is going to be a line that intersects a curve at 2 points. For example, given the parabola here, the yellow line on this graph would be a secant line because it intersects the parabola at 1 point here and another point here. So again, it intersects the parabola or the curve at 2 points. It's a secant. Conversely, a tangent line is a line that only intersects the curve at 1 point. So given that same parabola, we see that the yellow line is tangent because it only intersects the graph here at x equals 2. Again, one intersection is a tangent, two intersections is a secant. So now, what does the secant and the tangent line represent? How are those lines related to the curve? So a secant line represents the average rate of change between 2 points on the graph. So again, given that parabola in blue and the yellow secant line, the secant line will be able to allow us to find the average rate of change between x equals -2 and x equals 4. Or in other words, the average rate of change along the parabola between the two green lines. However, a tangent line now represents the rate of change of the curve at that singular point. So here, directly at the circled point x equals 2, this yellow line gives us the rate of change of the parabola only at x equals 2. Again, it's not the average of anything, but instead the rate of change at that one exact point. So now that we've discussed what a tangent is and what the tangent line represents about a curve, we can now talk about derivatives. So the derivative of a function f of x is another function, and that function represents the slope of the tangent line as a function of x. So for example, if we took the derivative of f of x and got a function, let's call it g of x for right now, g of x would give us the slope of the tangent line to any point on the curve. And rather than this giving us the average rate of change as a secant would, the derivative will give us the rate of change at a singular point. So going back to the previous example, if g of x is our derivative function, g of 2 would be the slope of the tangent line at x equals 2. And we could also take higher order derivatives. We're not going to go into this in too much detail in this video, but we could take things such as second derivatives, third derivatives, and so on. The second derivative, for example, would be the derivative of the derivative. So once we got that derivative function g of x I mentioned, we would then take the derivative of g of x and get another function. We could call it h of x. And that h of x would essentially be the rate of change of the rate of change of the function. So now, how do we notate the derivatives? As you'd expect from this line in the middle, there are two different ways we're going to do this. The first is the Leibniz notation. So let's imagine we have a function y equals f of x. In Leibniz's notation, the first derivative is going to be denoted dy dx. The second derivative is going to be denoted d squared y dx squared, and third and higher order derivatives are going to be notated dny dx to the n, and where we would plug in what order derivative we're taking for n. So for example, if we are taking the third derivative, we would put a 3 where these two n's are. Similarly, for the fifth derivative, we would write a 5 instead of an n. Now we also have the Lagrange notation, where y, and again, let's take a function y equals f of x. Here, the first derivative is going to be represented as f prime of x. We call this notation up here, that piece, a prime. The second derivative would be f double prime of x. So double prime, you would have two of those lines. And now for third and higher order derivatives, we're going to have f, and then we're going to superscript the order in parentheses and then have the x. So for example, if we want to write the fourth derivative, we would write f, and then we would have a 4 in parentheses. So f4 of x. This here would represent the fourth derivative. And which notation you want to use is really up to you. Some applications, one is better than the other, but for now, both notations are okay. So now we're going to talk again a little bit about the slope of a secant line. This may seem like a little bit of going back to algebra, but it will help us understand why we define the derivative how we do. So for a secant line, the secant line gives us the average rate of change between 2 points, and the slope of the secant line is used to get that average rate of change. So for a function f of x, we write the slope as delta y, or the change in y, divided by delta x, the change in x. And that's equal to f of x2 minus f of x1 divided by x2 minus x1. Again, assuming y is equal to f of x. But now I want to rewrite this a little bit. I'm going to define h to be x2 minus x1. So that means that the slope of our secant line would now become f of x1 plus h minus f of x1, and then that would just be divided by h. I know right now this looks more complicated, but again, bear with me, this will explain why the definition of the derivative is what it is. Now I should note that if we plug in h right now, we would just get 0 over 0. Therefore, something needs to change in this definition for how we get from a secant to a tangent. And to do that, we're going to do a little bit of an exercise on how we obtain the definition of the derivative. So let's imagine on this graph, we want the tangent at x equals 1 of the following curve. We want that infinitesimal change at x equals 1. So we can again approximate it using a secant to start out, and there's the slope again for the secant. So the first thing I'm going to do is, let's say h equals 4. So we're going to take the average rate of change between x equals 1 and x equals 5. Now, if we're looking for the average rate of change here of the blue curve, this is a pretty bad approximation when we use h equals 4. But now, when we make it h equals 3, we see that it improves a little. And this trend continues. If we set h to equal 2, and now we're only finding the rate of change between x equals 1 and x equals 3, we're starting to get pretty close in this region. We're now going to go a step further and set h equal to 1. So now we see that we're getting pretty close. The rate of change of the blue curve at x equals 1 is getting pretty close to the average rate of change, or the slope of the yellow secant line. And we see that while it looks very close to a tangent, it is still a secant because it intersects the blue curve at x equals 1 and x equals 2. However, nonetheless, we see that as h gets smaller and smaller, our secant line slope gets closer and closer to the slope of what the tangent line would be. And therefore, as h gets very small, we see that our secant line gets very close to being a tangent line. Or in other words, that our average slope becomes our rate of change at one particular point, which is what we're looking for. So lastly, we're just going to clean up and make a little bit more precise what was said on the previous slide. So again, as seen on the previous slide, as h got smaller and smaller, or more specifically approached 0, the secant line got closer and closer to being a tangent line, and as such, the average rate of change became closer and closer to what the slope of the tangent line would be. And since the derivative is the slope of the tangent line, that means that as h approaches 0, the average rate of change given by the secant line approaches being the derivative. So now, if we could mathematically show h approaching 0, we could relate the slope of the secant line to the derivative. So what we do here is we use the limit, because that's exactly what we use in math when we want to show that a quantity is approaching something else. So we're going to need to use the limit as h approaches 0 of our slope of the secant line. And that is the definition of the derivative. That the derivative, or f prime of x in the notation, is equal to the limit as h approaches 0 of f of x1 plus h minus f of x1 divided by h. And again, you'll see that this is just saying the derivative is equal to the limit as h approaches 0 of our slope of the secant line. With that, that concludes the video. Thank you so much for watching. Have a great day, and feel free to leave any comments you have below.